Okay, welcome everyone back to another semester of the Experimental Math Seminar. We are very pleased to have Neil Sloane, the OAS founder and visiting scholar here at Rutgers, talking to us about Eric Angelini's comma sequence. Please take it away, Neil.
Okay, I'm going to start off by playing a very short video made by, I'm going to be talking about Eric Angelini's famous comma sequence. And to celebrate his birthday, his son Lorenzo made this movie, which begins with the sequence.
I'd like to introduce you to the comma
sequence by Eric Angelini.
Goes like this.
1, 12,
35.
94,
135. 186.
248.
331,
300.
44,
87.
461,
175.
5.
130.
535.
590,
595.
600.
61,
667.
744,
791.
109.
997,
68. 149.
etc., etc., etc. Happy birthday to you. Happy birthday to you. Happy birthday.
Okay, good. So that was the video. And I want to stop sharing. How do I stop share? Okay, stop share. Okay, and now I want to share screen. So share screen. And with any luck, we'll see this, my keynote talk. Okay, which should be somewhere. It was there a minute ago. I don't see it. You can't see this, right, Robert?
Nope, not yet.
No. Somewhere there should be. Keynote, got it. Share. Okay, and now.
Looks excellent. Now
Okay,
press
so
play.
now we do play slideshow, and then I have to remove the list of faces just from me. More hide video panel. Okay, can you hear me?
Yes.
Okay, good. So I'm going to be talking about Eric Angelini's famous comma sequence. And, okay. Start with the video, done. Okay, so here's the sequence. How can I get rid of that nasty panel? Bring it down to the bottom. Okay, Eric Angelini, 2006, he defined something called the comma sequence, and it goes like this. 1, as in the movie, 1, 12, 35, 94, 135. And why is that the sequence? Well, the answer is you look at the commas between the numbers. Whenever you see a comma, you look at the digit to its left and the digits to its right. So that comma is surrounded by 1, 1. So the comma number for that comma is 11. The next comma is surrounded by a 2 on the left and a 3 on the right. So that comma number is 23. So I've written the comma numbers underneath the commas. And the rule that defines the sequence is that these comma numbers should be the differences between the terms. So after we have 1, we say, what's the next term? Well, the comma number, we don't know that it's that the comma number is going to be 11, but 11 is the first thing it could be, because the comma number for that comma must begin with a 1. So the smallest it could be is 1, 1. And if we try 1, 1, it works. 1 plus 11 is 12. Good. So now we're at 12. What's the comma number? Well, after this comma has a comma number which begins with 2. So it could be 21, 22, 23, up to 29. Only 9 choices. It can't take us long to find the right one. 21 doesn't work because if I put a 21 here, that would mean this number the next term would have to begin with a 1. Well, there's no way when we add 20-something to 12, we're going to get a number beginning with 1. So let's try adding 22. 22 doesn't work, but 23. If we add 23 to 12, we get 35, which begins with 3. That 3 matches the 3 of the common number. So indeed, it's 35, and that works. The next one is 94. We've got a 5 and a 9, and 35 plus 59 is 94, and that works. And so it goes on. The sequence itself is in NeoAIS since 2006. It's A of 121,805, a famous sequence number. And I must remember to turn off my phone now because all the junk calls that come in around now will be muted. All right. So the common numbers are that sequence. And when Eric sent the sequence in, he didn't know what would happen. He computed a few thousand terms, and it seemed to be going along very nicely, but he didn't know what would ultimately happen. So that was the sequence. Shortly afterwards, Edwin Clark noticed that it stops after a while. When you get up to about 2 million terms, 2137453 terms, which the term at that point is 6 9s 45, 9999945. The next term doesn't exist. There are only 9 choices for the next term after this, 50, 51, 52, 53, up to 59. None of them work. It doesn't, they just don't match in the way that they have to for the sequence to exist. So the sequence stops after 2 million terms. And this is, I think this is absolutely incredible, because this is a really simple base-dependent sequence. And you'd think if it gets going, then it's going to keep going. And so the fact that it goes for a large number of terms, I'm going to rotate the light so that it's no longer directly in my eyes. Yeah, okay, good. So it's really amazing that it stops then. And we have to say, what's going on? What I can say now is that it hit a landmine. 999999945 is a landmine. When you get to that, that does not have a common number, so the sequence has to end. Let me show you a simpler example. Suppose instead of starting with 1, we began with 3. Okay, what's the common number? Well, it's 30-something, and 33 works, and 3 plus 33 is 36. So starting with 3, the next term is 36. But now there's no choice for the next number. If you try 61, it fails, because if the common number was 61, we would get 97. And so the next term would begin with a 9, and it would be 69, which doesn't match 61. So 61 fails, and they all fail. So the sequence ends at 36. Now, for some reason, it won't let me go to the next page. If I do page down, no. All right, okay. If I click it, okay, here's the next slide. Just clicking it gives the next slide. Okay, so this is based on a paper that we've been working on for a month or 2 or more. It's a paper with 5 authors: Eric Angelini, Michael Branic, Giovanni Resta, and David Wilson. And it's very much a joint work. We've all contributed a lot to this, so I'm just the person giving the talk. Good. The arrows work. Okay, so just to give you an idea of what the talk is going to be about, as I said, this is a base-dependent sequence with remarkable properties, and we have a very good model for this sequence, for any of these sequences. You can think of them as a kangaroo hopping along an infinite road, making small hops, and occasionally there'll be a clump of landmines, like that number we saw, where if it lands on a landmine, the journey stops and the kangaroo dies, unfortunately. We know where the landmines are, theorem 1, and the conjecture is that the kangaroo will always die. All of these sequences are finite in any base bigger than 2. Base 2 is special. And we have a conjecture which Robert Bliss just told me he and Natasha have proved, I haven't checked the proof yet, but it says that the expected length of a comma sequence in base B is e to the 2b. And the conjecture, another conjecture, is it's always finite. A rule of thumb is that if the nth term is about n times b squared over 2, we have a very fast program. And now here's a really interesting point. Sometimes there are two choices for the common number. And Eric's definition says if there's a choice, you must always take the smaller. Well, it turns out sometimes there are two choices, not one. And it helps to change and take a different branch, to take the other branch, not the smaller common number, but the other one. And if you can do that, then there are infinite paths. And I've got little sledgehammers here showing where we actually use some powerful tools. The first sledgehammer is that we use Perron's theorem in getting this conjecture. And in this sledgehammer, we use Koenig's infinity lemma to prove that there is an infinite comma sequence. In base 3, we know everything. We know how to get to infinity with an explicit construction. And in base 10, we know there's an infinite path to infinity when we're using the choices. And we know 10 to the 84 terms. We don't know an explicit path. So those are the that's an outline. And here's a summary. I'm going to first talk about Landmines, theorem 1, and then introduce the two graphs. There's the successor graph, where you always do what you're told to do, pick the smaller common number if there's a choice. And the child graph, if there are two children, you have a choice for the common number. You get a graph which has forks in it, branch points. That's G sub C for the child graph. And that's a much more interesting, well, they're both very interesting. And then I'll show that the child graph actually contains infinite paths. That's a theorem. And then I'll talk briefly about the algorithm, which is based on the fact that the common numbers are actually periodic most of the time. And the final section will be about the chance of the kangaroo hitting a landmine and its expected lifetime. So, as I said, if you start at 1, the sequence goes for 2 million terms. And it reaches this landmine, and it dies at that point. If you start with 2, the comma sequence goes for about 10 to the 15 terms when it reaches another landmine and dies. On the other hand, as I showed you, if you start with 3, it's only 2 terms, and it reaches 36, the landmine, and it dies. If you start at 4, it goes for that many terms. If you start at 6, it goes for about 10 to the 18 terms and reaches this landmine. I start at 7. So these are two sequences that really are remarkably irregular. You have to say, this is a really interesting question. What on earth is happening? How could we have such tremendous fluctuations in lengths? And so let me remind you of the definition now. We know what the common number is. It has the property that it's the difference between two terms. So in other words, the next term, a of n plus 1, is the term you're at plus the common number. So this is the recurrence that defines the comma sequence. And I'll call the next term the comma successor. And the common number is the common number that you add, the number surrounding the comma between the two terms. Now, a very important observation is that if the leading digit doesn't change when we go from a of n to a of n plus 1, if they have the same leading digit, then you can say precisely what the common number is. Because suppose we're at a of n, which has decimal expansion b, c, d, e, f, say, then the common number we know begins with the last digit f, and the next term, if it has the same leading digit b, then the common number is FB, 10 times F plus B. And so we know explicitly what the common number is if the leading digit hasn't changed. And that's what makes it possible to compute these astronomical numbers of terms, that observation. We can shortcut the algorithm. We don't actually have to work out all those terms. We can jump to the next time when the leading digit changes. Another observation is that the common number is never too big. It's a two-digit number. In base 10, it's never bigger than 99. In base B, it's never bigger than B squared minus 1. So the kangaroo hopping along the line, the comma sequence going on its merry way, just increases slowly. This is not like the Fibonacci numbers, which grow exponentially. But also, we don't have to kill any rabbits this is ecologically more friendly than Fibonacci numbers. Fibonacci numbers uses exponentially many rabbits. The comma sequence just uses commas. Commas are free. So it grows slowly, but no rabbits are harmed, just an occasional kangaroo. So the average steps, so the steps are two-digit numbers. Their average is B squared over 2. So most of the time, on the average, you're adding B squared over 2. So a rough rule of thumb is that the nth term is about n times B squared over 2, about 50n if it's a base 10 sequence. B is 10, B squared over 2 is 50. So roughly speaking, in base 10, if the sequence doesn't die, it's going to grow at about 50 times n. And here's a plot. This is a graph of, let me move this. I can move that. Okay, so I can now see that. So here's a plot of A of n over n for the original Angelini comma sequence. And you can see it does roughly approach 50. But it's not a very smooth thing. So this is a really crude approximation, but it's useful nevertheless. If it doesn't die, the comma sequence is about n times B squared over 2. Right. Thank you. Now the landmines. Theorem 1 tells us what the landmines are in base B. And let me tell you what they are in base 10, because that'll make it clear. In base 10, there are 8 landmines with 2 digits, 18, 18, 27, 36, 45, 54, 63, 72, and 81. They're the landmines between 1 and 100. If the sequence reaches any of these, the sequence, you remember, starting at 3, reached 36, and it ended there. If you reach any of these, you end. The next group of landmines, you can put a 9 in front of these, giving you 8 more landmines. The next group, you can put 2 9s in front, and so on. You can put any number of 9s in front of any of these 8 numbers, and those are the landmines. So they're quite sparse. I took a piece of log linear graph paper and marked with asterisks where the landmines are. Between 1 and 100, there are 8 of them spread out like this. Between 100 and 1,000, they're all in the range of between 900 and 1,000. They're all very close to the end of this range, the end of this, I think of it as a century. In the next century, from 1,000 up to 10,000, all the landmines are very, very close to here. And the kangaroo, the poor little kangaroo, is hopping along and making small jumps, and it's trying to get as far as it can. It actually, it doesn't have any choice itself. Once it's started, it has to follow the comma rule. So it goes along. And here's the proof of theorem 1. It's easy and good. Now, sometimes there's a choice. If there's a choice, Eric's rule says you've got to pick the smaller of the 2 choices. Let me show you an example where there's a choice. Suppose the comma number started, suppose the sequence started at 14. What comes after 14? What's the comma number for 14? Well, there are 2 choices, it turns out. It could be 45, because 14 plus 45 is 59. The difference is 45. Or it could be 46, in which case we get 60. If there's a choice, it's always like this. There's a difference of 1 in the common number, and the leading digit of the next term it changes by 1. There are sometimes 2 choices for the common number, but never more. And when does that happen? Well, there's that's theorem 2. We can say precisely, sort of, what the common numbers are. Now, in this case, we know exactly what the common numbers are. There are 2-digit common numbers which are special, namely 14, 33, 52, and 71 in base 10. The formula is Wx, where x is anywhere between 1 and b over 2, the base over 2, 1, in this case 1 and 4. 1, 2, 3, 4, and then the first digit is 9 minus twice that digit. So 5 plus twice 2 is 9. And then you can insert, you can double up the initial digit. So the next bunch look like this: 1, 1, 8, 2, 2, 7, 3, 3, 6, and so on. And then you can insert 9s, and you get things like 191, 1918. So this is where the sequence splits, and we're forced, in the strict case, to pick the smaller of the 2 numbers. But in the graph, there are 2 outputs. Officially, you know, the law of primogeniture says that the firstborn child is the successor, the heir to the throne. So we're consistent here. The firstborn child, meaning the smaller of the 2, is the successor, and the other one is the rival child, the elder child, the rival to the throne. And so if we define 2 graphs, I think things become a lot clearer. The successor graph just tells you what the successors are of each number. The successor graph, you join x to y if y is a successor to x, the smaller child if there's a choice. In the comma graph, you put in both possibilities. So there's a decision point here, a branch point, where we could take the smaller child or the larger child. That's GC, the child graph. So base 2 is special. Base 2 is quite interesting. If you do this in binary, the sequence goes 1. You can do this in your head. What's the common number for 1? Well, 1 in binary, the next term has to begin with a 1. All binary numbers except 0 begin with a 1. So the common number after 1 would be 1, 1. And when we add, which is 3 in binary, when you add 1 and 3, you get 4, which is 1, 0, 0. And so 1 goes to 4 and goes to 5. And you get an infinite sequence beginning at 1. And if you begin at 2, you get the complementary sequence. Here you get numbers that are congruent to 1 to 0 or 1 mod 4. Here you get the others congruent to 2 or 3 mod 4. The successor graph in base 2 just has 2 connected components, and they're infinitely long paths. But that's special. In base 10, the successor graph, as I will show you soon, it turns out it has exactly 50 components. No, it has infinitely many. I'm a little confused. Why did I say there are infinitely many? There are actually only 50. This is wrong. There are 50 finite paths, and there's no infinite path. That's a conjecture still. We don't know that there are only finitely many paths. So if you're looking at these paths, you want to know, where did they begin? So a useful lemma is that if we have a number n and we ask, is it a child of some earlier number by the comma rule, then the theorem is there is a child, and we can say what it is. The parent. if n is the child of k, then we can say precisely what k is. K is n minus 10b minus 1 minus f, where f is the first digit of n and x is n minus f mod 10. And so that's what the parent is. And if it exists, it's unique. If this number turns out to be negative, then it wasn't a child of anything. And if another observation is, if it is a child, it might not be the youngest child. It might not be the official successor. So we have a theorem that in base 3, we can say exactly, in any base bigger than or equal to 3, we can say exactly what the parents are, what the comma successors are. Sorry, we can say which numbers don't have successors. Let me show you what it is for base 10. So in base 10, sequence, I didn't write down the sequence number. In base 10, there are infinitely many numbers that don't have parents, that are not successors. And there are a certain set of numbers, 2-digit numbers, which are a bit irregular, and then numbers like 200, 300, 400. And you can easily check, for example, that 200 is not the child of any number. It's not, it doesn't have, it's not the successor of any number, but it is the child of a number. So there's a number which has 2 children, the eldest of which is 200. So it's not a successor, but 200 is the child of a number. So so the numbers that are not successors in base 10 are these numbers, infinitely many of them. If we ask which are not children, then all of the numbers bigger than 100 go away. 200, it's not the successor, but it is the child of a number. And so when we look at the numbers that are not children, they're all in the range 1 to 99. In general, in the range 1 to b squared minus 1. And in base 10, here they are. These are the 50 numbers that are not children. So these are the 50 root nodes in the comma graph. And so now we can have one of our big theorems that it says that in the child graph, in any base bigger than 2, there's an infinite path. And the proof is, from what I just said, every number belongs to a tree whose root is less than or equal to 99, in general, less than or equal to b squared minus 1. So we have an infinite graph. It's a collection of rooted trees, and the roots are at most 99. There are 50 of them in base 10. So because there are only finitely many, by the infinite pigeonhole principle, one of these components must contain infinitely many nodes. So that component is a rooted tree with infinitely many nodes, and when it branches, it can either, there are only 2 choices for each branch. So it has, it only has finitely many branches, it's locally finite. And so we can apply Koenig's infinity lemma that says precisely that in this situation, there's an infinite path that starts at the root and goes to infinity. And this is, if you want to read about this very nice theorem, then there's a really excellent book by Hal Bison, Combinatorial Set Theory. And so the moral of this is, if we're allowed to choose which child to follow, then we can avoid all the landmines. We know it's possible to avoid all the landmines. This is just an existence theorem. It doesn't tell us how to do it. So let me speak a bit about the base 10 child graph. This is a collection of rooted trees. We know there are exactly 50 of them because every number in base 10 is what has a parent, which is one of 50 numbers in the range 1 to 99. And if the parent was 1, the first sequence I mentioned, Eric's original sequence, starts at 1 and goes for about 2 million terms and ends. Well, it turns out, you can check by computer, that if you start at 1 and follow all the branches, they all die within 10 to the 25th terms. So the component, which has root at 1, is a finite tree. If you begin at 2, again, you check by computer, the highest tree you can get has height 10 to the just under 10 to the 16. Every path starting at 2 ends by 10 to the 16. When you start at 20, you find that there are paths that escape. The one that gets furthest before dying is starting at 30. If you start at 30, you can get out to 10 to the 365 before you die. But eventually, every path starting at 30 dies. So we know there's an infinite path beginning at 20. And we don't know how many there are. It seems very likely there's only one, because in base 3 we can actually prove there's only one, and probably the same proof will work at base 10, but it'll be finitely more complicated to do it. So just to be safe, we'll define the sequence A367620 is the earliest infinite tree in base 10. We know it exists. We know it starts with 20, and we can follow it for quite a long time, because the first branch point, if you start at 20 and follow the comma rule, the first time you have a choice is after this many terms, when you reach a branch point at 1,999,918. And the correct thing to do when you get to that branch point is to take the lower branch. And then you keep going and you come to another branch point. And again, we've found out that you should take the lower point, the lower branch. And we've followed these branches and all of their possible outcomes for 60 through the first 69 branch points. And the sequence that tells you which branch to take is this binary sequence, 001100111101, and so on. And this is not in the OEIS, and I don't see any pattern to it. When we did this in base 3, there was a pattern. The pattern of choices that worked was 01010101. And we've now been able to prove that that's the right choice. That gives you an infinite path. Here, all we know is the first 30 branch points. You should do this. We've followed them out to 69, and there are half a dozen or so that still survived. So we don't know what will happen to that. And the reason we were able to compute so many terms is that the common numbers, the first differences, are periodic. Let me just show you a little picture here. Here's a typical calculation. Here's Angelini's sequence, the main comma sequence. And after 1942 steps, you get to 99987, and then the leading digit changes. And the next number, this has common number 61. The next number begins with 1, 100,058. And you get it by adding 61 to that. This has common number 81, and you add 81 to 10058 and get 139, and it ends in 9. And so the next common number is 9. The leading digit isn't changing. So all of the common numbers end in 1, and the first digit of the common number goes up by 1 at each step. So the common numbers for this particular point in this particular sequence are 8191 ... 71. It's a set of 10, these 10 numbers, which repeat over and over again. Now the sum of these is 460, and there are altogether 2,171 terms between here and here. So we can say we're going to get 217 sets of 10, contributing 460 times 217, which is 99901, and then there's one more, which is the next 81. So the total that we've added, so I forgot to say, this string of numbers that begin with 1 ends after 4114 steps, and we get a number beginning with 2. So this observation makes it possible to shortcut this whole calculation. We don't have to follow this. We can say exactly what's going to happen. So instead of doing 4,000 steps, we just do 1 or 2 steps, and we can say we've gone from this number, we've added 217 times 460 plus 1 more, 999. So add them up and you get this. So this shortcut makes it possible to speed up the computations a great deal. And that's the basis for the algorithm. The last section is, what's the chance of a kangaroo hitting a landmine? Can we say how long it's going to live on the average, the poor kangaroo? So let's look at what happens when we're going, say, from 100,000 to 1 million. The kangaroo, from 1 power of 10 to the next, I call that a century, from the period from 10 to the k to 10 to the k plus 1. What's the chance that the kangaroo, once it gets past 10 to the k, will make it all the way to 10 to the k plus 1? It will, if it doesn't hit a landmine. There are 8 landmines, and they're all in the last 100 cells of that range. So once it starts, it'll very easily get to 999900 if k is 5. And then from then on, it's in danger. It may or may not hit a landline. So the calculation, what we did was we said, okay, let's suppose it lands. It starts off in the range, in this range, at a square S, which is anywhere, is one of the 100 numbers in the last 100. It jumps in, it lands at S, and then it follows the comma rule, and either it gets beyond it gets into the next power of 10 range, the next century, or it dies. Well, this is a simple calculation, and the answer is, out of these 100 numbers, 88 of them manage to get to the next century, and 12 of them die. 8 of the ones that die are the landmines, and there are 4 other numbers in this range which lead to a landmine and die. So if you pick a starting point at random and come along, the chances are that 12 out of 100 tries, chances you'll die, and 88 chances out of 100 you will succeed in living to the next century. And so the chance of death for each century is 12 over 100, 1 over 8.33. So the expected number of tries before we actually hit a landline is 8.33, which will put us into the interval around 10 to the 8.33. So we can say the average life of a base 10 kangaroo is 10 to the 8.33. And that kind of matches the data. Those irregular numbers that I showed you at the beginning, well, 10 to the 8th seems to be a rough, it's not surprising that that's the mean life. Although the variance, which we don't know the variance, it seems quite large. Now, what about other bases? This is base 10. In base 10, the chance is 12 over 100. So I computed the chances for other bases, for bases up to 100 actually, and I got a sequence. For base 10, the answer is 12. For base 9, the 11 starts that die, and so on. So it's a sequence. I've marked it with an asterisk. It's not in the OAIS, and it's still not in the OAIS. but it probably will be soon. It's not in the OAIS, but its differences were, its first differences matched an existing sequence. And, you know, this is the first time in all this project that a sequence has turned up, which is already in the OAIS. We've added something like 70 or 80 sequences connected with the common numbers problem, and none of them were in the OAIS. This is the first time that's happened. I didn't have a proof that these numbers actually matched this sequence. They match it for the first 100 terms, but I didn't have a proof that they match in general. But Robert Bliss sent me an email just an hour or two ago saying that he and Natasha can actually prove that they match, which is very nice. But the moral of that is, in base B, the chance of the kangaroo dying is the nth term of this sequence over B squared. And the sequence is, the differences match A136107. So the partial sums of that are the generalization of 12 for base 10. And I wanted to know how that grows asymptotically. A136107 has some very interesting properties. This definition is, it's the number of ways of writing n as the difference of two triangular numbers, n being the term here. But actually, I'm using B because we're looking at what happens as the base increase. So the 13617, the relevance is that the nth term of that is the number of ways of writing B as the difference of two triangular numbers. And I asked Václav Kotezevich, who is one of our editors-in-chief, who happens to be very good at finding asymptotic expansions. I asked him, could he work out the asymptotic expansion of the partial sums of this sequence? And he said, yes, it's not that difficult. You just use Perron's theorem. And so here's what he did. We want the growth of that asterisk sequence, and there's the partial sums of that sequence. Now, that sequence turns out to be the difference between A of 1227 and A of 10054. The latter one is the characteristic function of the triangular numbers. It's zeros and ones. Its partial sums are negligible, so we can forget about that. A of 1227 is much more interesting. It's one of the classic sequences. It's the number of odd divisors of n, or of B in this case. And it has a nice ordinary generating function, and it has a nice Dirichlet series, a nice Dirichlet generating function, which is, it's the number of odd divisors. The Dirichlet series is zeta of n times 1 minus 1 over 2 to the s. You want to get rid of the even divisors. And then Perron's theorem says that the partial sums of this, Perron's theorem tells you what the partial sums are of a sequence if you know its Dirichlet generating function. And the answer is it's the residue of the pole at 1 of the Dirichlet generating function times b to the s over s. And you ask Mathematica, and Mathematics says that is b times log 2b over 2 plus the Euler gamma constant minus a half. So what's the chance of dying? When we go from b to the k to b to the k plus 1, the number of deaths is given by this formula. And we can replace log 2b by log b. It doesn't make any difference. So it's b log b over 2, basically, and divide by b squared. And you get log b over 2b. So the chance, the expected number of centuries you get through is 2b over log b. And so the expected life is b to the 2b over log b, which you take the log b up here and it becomes e to the 2b. And so that's the conjecture, which, thanks to Robert, may now be a theorem. And thanks to Václav for doing the analysis. And that's basically the end. The main unsolved problems are that I can't tell you exactly, we can't tell you exactly, if I say we've got a base 7 comma sequence that starts with 3, how long will it be? We don't know. We can't say exactly what it is. We can say what the expected value is, but because the invariance, if is surely very large, we don't know exactly what it is. Another open question, which looks hopeful actually. In base 3, we can show that all of the classical comma sequences, no matter where you start, they're always finite. And we can also say what the path to infinity is. It's unique in the child graph, but in general, we don't have a proof that there's no infinite path in the successor graph for bases bigger than 3. And the other thing is, in base 10, what actually is the infinite path? How do we get to infinity? We know the first 10 to the 85 terms and the first 30 decisions, but we don't know. So that's the end of my talk. Are any questions?
Everyone, first let's thank Neil for the excellent talk. Okay, some thunderous applause. Any questions for Neil?
I'm sorry, I don't know how to put back the face, the thumbnail pictures of the people, so I can't see anyone. But if you have any questions, please.
Neil, maybe I have a question to start. It feels sacrilegious to ask you, are there sequences that you haven't put in the OAAS? But I did notice that the partial sums were not yet in the OAAS. Do you have other sequences from the project that you're waiting to submit to the database?
No, I was waiting on that one to see if anyone had found a proof.
Okay.
No, I've been putting in all the others, and there are something like 70 or 80 sequences that have come out of this project. And it's interesting. That's the only one that has any connection to the outside world, to any other problem. And you know, my philosophy is that when you have a nice problem and it produces some sequences, you should look them up in the OEIS. And if they're not there, you should add them, because sooner or later they're going to be connected to some other problem and someone will be grateful. So it was very interesting that there were so many sequences that came up, and none of them had any connection with the outside world. This is the first time it happened. So if you look at the graph that connects sequences in the OAIS, if they're related in some way, this comma sequence is its own an isolated connected component, which is now connected by one edge to the rest of the graph.
Hi, Robert. I have a question.
Please, Dorian.
So you showed 53s for the child graph,
Yes.
right? And you said the first infinite one was at 20. How many of these are infinite?
That's the only one. Well, out of the 50, 49 of them have only bounded trees. The only, I think it's going to be unique, but the only component that has an infinite path is the one with the root at 20. And
Neil, could you explain again how you prove that?
Yeah, we looked at the tree. Say we begin with 1. We look at the child graph, and it goes along, and I forget where the first branch point is, but we followed all the branch points until they died. That's how. Brute force.
And that was the only one left that hadn't died. So
starting at 20, yes.
right, starting at 20. So it had to be the one.
The one, yeah, exactly. Starting at 30 was the one that made its biggest attempt to escape. That got out to 10 to the 350 terms before all of the paths had died. Brute force.
Any other questions for Neil? No? Okay, well, let's thank the speaker one more time for an excellent talk.
Hooray!
All right, thank you everyone for coming out. We will be back in 2 weeks with another talk. Until then, have a good couple weeks.